We'll now put a lot of the material developed in this course to work in a concrete case study. The task is to find a purely functional solution to a well-known problem, the so-called water pouring problem. Another variant of the problem is found in the course by Peter Norvig called Design of Computer Programs on Udacity, where Peter develops a very nice solution in Python. The solution developed in our course differs from his in some respects. First, it's purely functional, and second, it's also more general. You might find it instructive to compare the two solutions, if only to see that there are different ways to skin a cat. The final program we're going to develop in this course is a solution to a well-known problem called the water pouring problem. The idea is as follows. Let's say you're given a faucet and a sink and a number of classes. Right now I will just draw two of them of different sizes. So just for the sake of the example, let's assume this glass has size 4 deciliters and this glass has size 9 deciliters. What you need to do is produce a given quantity, let's say for the sake of the argument 6 deciliters of liquid in one of the glasses. Doesn't matter which one. However, you're not giving any marking on the glasses, so the only knowledge you have is the total capacity of the glasses. And the moves that are available to you is you can either fill a glass completely using the faucet, or you can empty it in the sink, or you can pour from one glass to the other until either the glass from which you pour is empty or the glass into which you pour is full. Now the classical water pouring problem uses two glasses of the given sizes and the given target size of 6 deciliters. But we are going to generalize that a little bit. We want to have an arbitrary number of glasses of arbitrary given capacities and an arbitrary target capacity in one of the glasses. So let's see how we would model this problem. First, how do we represent the state of the glasses? Well, the idea would be to represent a glass as an int, ranging from 0 to the number of glasses minus 1. And then our state would be a vector of int that would give us for each glass the number of deciliters that are in that glass. And then the question is, what kind of moves do we have? Well, we have 3. You can empty a glass, you can fill a glass, or you can pour from a glass to another glass. So let's see if we have, let's say, the 2 glasses of size 4 and 9, and we start in a state where both glasses are empty, so that would be the state 0 and 0, how that would evolve. So one thing we could do is we could fill glass number 0, and that would bring us into the state 4 and 0. Or we could fill glass number 1, and that would bring us into the state 0 and 9. From there on, we could pour, starting from this state here, from glass 0 into glass 1. That would give us the state 0, 4. The action would be pour 0 to 1. Or we could, for instance, pour 1 to 0 here. Then we would end in a state where the first glass has capacity 4, it's full, and the second glass has 5 ounces in it, because that's what remains. Sometimes moves lead back to states that we've visited before. For instance, if we empty the glass 1 in this state here, then we would be left with the state 4, 0, which we can also reach shorter by just a single move here. Now you've seen how moves pan out. The question is, how do we find now the right solution? How do we generate moves so that we find the right sequence of moves to lead us to our target capacity? Let's say that's 6 here. So now that we know what moves are, let's see how we can use them to find a solution to our problem. The idea would be that we generate all possible move sequences, call them paths, until we hit on one that contains one of the glasses with the right target amount of liquid in it. So We would then start from an initial state of all classes empty, and then generate all possible moves to new classes. And once we have generated all possible moves of length 1, we would generate then all possible moves of length 2, and so on, like an onion, until possibly we hit on a path where we would have one of the classes with the target amount of liquid in it, in this case 6. The idea then is that we generate these path sets from inside out, starting with the shortest ones and progressively lengthening the paths until we hit one which is the right one, or, that's another possibility, until we have exhausted our search space and there is no solution. So now that we have an idea for a solution, let's see how we can put it in code using the Scala Eclipse IDE. What I'm going to do is I'm going to create a class, call it pouring, to contain the elements of the problem. So pouring should take as a parameter a vector of all the glasses and their capacity. So that would be a vector of int, one entry per glass, and for each entry its capacity. The first thing I'm going to do is I'm going to work on states. So what is a state? Well, a state is a vector of integers. One thing we could do to make that clear is make a type alias saying state equals vector of int. The next thing to do is, well, let's define what the initial state is. So the initial state would consist of all empty classes. So what we're after is a vector of the length of capacity consisting of all zeros. There's several ways to do that. Probably the most elegant way would be to use a map. So what should I apply in the map? Well, it's a function that takes a class, an integer, and returns 0 for any integer it gets. Good, so now we have the initial state. How can we move from that state? Let's define what our moves are. The idea there is that I would have a class for each move. Let's make it a case class for convenience, and they all would inherit from a common base trait move. So we would have a trait move here, and I would then define 3 case classes, empty, fill, and pour, that all extend move. So now that we know what types of moves are available to us, we still need to generate all possible moves. So all possible moves would be empty an arbitrary glass, fill an arbitrary glass, or pour from an arbitrary glass into another. So let's generate those. As an aid here, I have defined one auxiliary data structure, all glasses. That would be a range that goes from 1 until capacity.length. So what would the possible moves are? Well, one way to do that would be to define it as 4 expressions. Let me do that. So I would say for g taken from glasses yield empty g. So those are the first moves available to me, empty an arbitrary glass. Other moves are for g taken from glasses fill g. And finally, for from taken from glasses to taken from glasses, if from is different from to, we can't pour from one glass into the same, then yield pour from and to. Okay, so let's set up a test to see what we have so far. I'm going to create a new worksheet, call it test. And what I'm going to do is I will set up an instance of my class. We have to define a vector of initial capacity of glasses. Let's say The first class has capacity 4 and the second has the capacity 7. And now what I want to do is I want to say, well, what moves are available to me? And what we see here is I get a vector to say empty 0, empty 1, fill 0, fill 1, pour 0, 1, pour 1, 0. So those are all the moves that I have. But of course I could also generate another class. Let's put another class 9 in here. And then I would have more moves that you can see over here. So 3 empties, 3 fills, and 6 pours. Back to our class. The next thing to consider is how moves change states. There are a number of ways we could record that. What I'm going to do here is I'm going to write a method change in the move trait that will have to be implemented by each case class. So change is defined on a move and it takes a state and it gives us a new state. So that would track how each move changes the state. Let's implement this method for each of our case classes. So for the empty case class, how is the state changed? Well, what the new state would be the old state with the updated method, so that does a change at one point in the state. At what point is it? Well, at my class, which now will be empty. So it's the old state updated at the point of the class where it's now empty. But remember that updated doesn't destroy the state. The old state will still be available. It's just a new state object that gets generated by this updated method. Updated is a purely functional method here. Good, so let's see for fill. Here our change would be that the glass is updated not to be 0, but to be full to its capacity. So glass gets updated to capacity of glass. And finally for pour, there the problem is a bit more complicated because it depends whether one glass can fully fit into another or not. So what I want to do is I want to first define the amount that gets poured from one glass to the other. So what would that be? Well, it could be that we take everything that is in the from glass in the given state, provided that there's enough room in the to glass. Or if there's not, then it could also be that we fill the to glass to its capacity. So it would be state of capacity of 2 minus state of 2. So the amount is the smaller of the current filling rate of the glass we pour from and the free space in the glass into which we pour. Now that we know the amount to pour, the state can be updated straightforwardly. So it's the old state updated at the from glass, where the new value of the from glass is the previous value minus amount, and the new value of the to glass is the previous value of the to glass plus the amount. So now that we've seen moves and the changes they do to states, it's time to look at paths. So paths would be sequences of moves. I'm also going to define a class for paths. So I define a path by its history, which is a list of moves. And the idea would be that the history is taken in reverse. That makes it easier to extend the path with a new move. So that means that the last move in the path comes first in that history list. So what are useful operations on a path? Well, one operation I would be interested in is what state does it lead to. So let's define that end state. And well, that would be a state. How do I define that? Well, one way to do it would be by a pattern match over the history list, and that would be a recursive function. So let's try that. So let's call this track state of history. And we would have an auxiliary function which would be defined by a pattern match over our argument list. If the argument list is nil, then we return the initial state. If it consists of a move and some remainder x as 1, then what we would do is we would track the state of the remaining list. Remember, the last move comes first in the list. And then we would apply the first move to change the result of that. So that's simply move, change the result of track state, because track state returns a state and move has a change method that changes the state to give the new state. So that computation of end state works, but let's look at it closer for a moment. Let's look at it graphically. So what we've done here is we have essentially done a set of changes with moves where each recursive call is a previous version of the history, until initially, when the list is nil, we return initial state. So what does that remind you of? Well, it's a fold right. So it's a fold right where we go through the list and we combine it each time with the change operator. So we can reformulate it as follows. We take the history, we do a fold right. The initial state at the lower right is initial state, and our operation is the one where we take each move from the history and we change each state on the right. And that will do exactly the same thing. Now the new formulation is without a doubt much shorter, and some would argue more elegant than the recursive pattern matching solution. But for most people, in particular beginners, it's also much harder to come up with and maybe to read. So if you or your team would decide at some point that you prefer the recursive explicit pattern matching solution, that's perfectly okay. So what we can do now is we can delete our previous auxiliary method track state. We have now condensed it into the fold right and obtain a solution that's much shorter for paths. So what else do we need to do on a path? Well, one useful operation is no doubt to extend it with another move. And that would just be a new path where the move precedes the history that we have so far. And finally, it's always good to be able to print objects in an intelligible manner. So let's define a toString function. So to print a path, we want to print its history, but we probably want to reverse it first. So first moves first and later moves later. And we want to print it, let's say, with a space between different moves. And finally, it's also good to know where the path leads to. So we are interested in its end state. So let me write it this way. So that was paths. Well, let's define the initial path. The initial path then would be the path that contains the empty history. Now with all the elements that we need for our solution, let's take a quick look at the diagram. So you see here that we would have a method that extends a set of paths with new moves successively of longer and longer lengths. So the way we would put that in code is that we have a function very similar to the from integers, only now we don't start from an integer and so generate all successive integers. We start from a set of paths and we generate a stream of set of paths. So that means we generate longer and longer sets of paths in a stream. So one thing to take care of is the boundary condition. What if paths is empty? Well, in that case, there's nothing to evolve, so we should return the empty stream. If paths is not empty, what do we do? Well, the idea is we need to generate all the possible new paths that have the paths in the set as a prefix. And from then on, furthermore evolve the stream. So let's do the first thing first. So let's call the new paths more. So more gets generated by a for expression. We let path iterate over all the paths in our set. And then for each of them, we generate a next path by extending the current path. And extending the current path we do with all possible moves. So the way we do that is that we have the call moves map path.extend. For each of the possible moves, we apply the operation extend with that move to the path, and that gives us a new path. And all those next paths would yield my more set. Now that I have my next generation set more, I can use that to define the full stream that starts with the given path set, and that is followed by the evolution of my next generation more. So it would start with paths, then more, because that would be the paths for the next iteration from more, then more of more, so twice paths of length 2 added to paths, and so on. So that's my path generating function from. I can use that to now define the set of all possible paths. So let me call that path sets. And that would be from applied to the set that consists only of the initial path. So what that set gives us is, in the first set it gives me set of initial paths. In the second element it gives me the set of all paths of length 1 that start with initial path, then all paths of length 2, and so on until infinity. So now that we've that much, we can have a quick look in the worksheet to see what we get. So let's take our problem and take all the path sets, maybe reduce the size of the problem like this. So we would get a stream which is the vector of 0, 0, and then because it's a stream it doesn't evolve any further. So let's do the usual trick and say let's take 3 elements and convert to a list and see what we get. And we get an impressively long list of possible moves that are all the moves that we generate here and the end states. So now that we have all possible paths, let's see how we would find the solutions. So let's define a function solution. It takes a target, which is the volume that we want to see in one of the classes, an int, and it should give us back a stream of paths that have the target volume in their end states. So how would we go about defining that function? Well, the idea is to go through all the path sets, and from each of the path sets pick the paths that are solutions, that have the target volume in their end state, and finally to concatenate them all in another stream. So the result stream would then consist of all solution paths ordered by their length. So let's do that. So it would be a for expression where we first go through the path sets, which are taken from the path sets value here. And then for each path sets we go through all the paths in that set, and then we want to demand that the path is a solution. So what would that be? Well, it would be that the end state of the path contains the target volume. Then the path is a solution, and in that case we return it in the resulting stream. Now that we have the solution sets, let's put it to a test in our worksheet. Let me define problem.solutions of, let's say, 6. And I get a solution. Let's see what it is. So here we would have a sequence of moves that yields the vector 4, 6. That's fine. Let's try something else. Let's maybe try the original problem with 9. And then we see it unfortunately takes already a long time. That's not so good. So it seems we have found a solution, but not a very efficient one. So let's go back and see what the problem could be. So one problem is, if we look at the diagram, that we move blindly. That means we generate from each possible state. Let's say we have a state here. We generate new states, but we will also generate a lot of old states. So we do a sort of random walk on the states, constantly revisiting also old states. And these old states don't really bring anything to the solution, because when we go back to an old state, that's not a path we want to consider, because by definition, there is a shorter path that leads to the same state. So the problem we have is that all this exploration is rather aimless, and a better way to do it would be to exclude any state that we have visited before. So let's try to do that. So the idea would be that in my stream generating function, I would have a second set, now a set of states that represent the explored states. And I will now restrict my moves to those that don't lead to a state that's already explored. So what I would write here is, let's say, explored is not allowed to contain the end state of next. Now I still have to fix up some bits that now yield type errors. So the first thing is, in the recursive call to from, I have to pass a new explored set. So that would be the old one. And also for each of our moves, our path, and also for each of the paths in more, its end state. So that would be more map end state. Finally, for the initial call to from, I would have the set of states that's initially explored is just the initial state. Okay. So with that solution, we can try again. And now we have a solution to this problem, which is slightly longer than the one we've seen before, also in very little time. We can also try something else. We can add more classes, such as, let's say, 19, and we want to find 17. And we can try that, and again, we would get solutions fairly quickly. Let's look at the problem again. We have a workable solution. It's reasonably efficient. Can we make it more efficient? Is there still room for optimization? Well, one area where we could optimize is the end state method. So end state gets called a lot, you see, in the exploration of possible solutions. And each end state is a fold right over a complete history, so a recursive function over the history. As paths get longer, end state becomes more and more complicated to compute. There again, you could say, well, why recompute the end state of a path? Can't we just store the end state once and for all in the path, and that would avoid the recomputation? So let's try that. So what I'm going to do is I'm going to put the end state in the path. That means I can remove it here. And because it should be available from the outside, I make it a val parameter. So now I can see it. And now I have to compute a new end state when I compute a new path. So what would be the end state be of the path that consists of the given move last and the history before that? Well, it would be the change effect on the move on the previous end state. So that's the new one, where if we add a move to a path, then we add the new end state that consists of the change effect of the move on that previous end state. And the initial path then would be, the end state is the initial state. And if we do that and test it again, we find the same solutions, and maybe it's a tad quicker. It definitely will become more apparent as paths would get longer. So that completes the solution. So what we did is we modeled the problem in a class pouring. We first modeled states, then we modeled moves and the changes they have on states, and we generated all the moves in this variable here. Then we modeled paths as their own class, and finally we modeled the state exploration function from as a for expression, and the function that picked out all solutions from the generated paths as another for expression. So this was quite a complex program. In particular, there's a large choice of representations. So we picked specific classes for moves and paths, but we could also have taken some encoding. We picked object-oriented methods. We could also have done some naked data structures with functions. Present elaboration is just one solution, not necessarily the shortest ones, but I believe it's actually quite clear from a domain modeling standpoint. Now you might ask, what are good guiding principles for a program like that? In the end, it comes down to experience. As the saying goes, you can learn programming in 10 days and then you improve for 10 years. But there are a couple of guidelines anyway that are useful. So I believe the first guideline is name everything you can. Functional programming is great because it allows you to break up things in really small pieces, expressions that consists of maybe just 3 words. Make use of that. Some of the assignments I've seen have crammed a dozen or more operators on a single line, taking advantage of the conciseness of functional programming in Scala, but I don't actually think that's good style. So break things up in little pieces, give a name for each piece. That makes programs much more intelligible and readable. So for instance, we put the change method inside the move classes because a move changes things. So it makes sense to define change right where you have the move. And finally, when you do a design, keep in mind that you always want to keep degrees of freedom for future refinements. So think of what might change in the future and how you could encapsulate the implementations from clients so that you could change it in the future without changing any of the client code.